Okay, I think we are ready to go. Hello and welcome to my presentation about enabling TrenchBoot in Xen Hypervisor. My name is Michał Żygowski. I'm a firmware engineer at FreeMDep, a company based in Poland. I mainly do BIOS and firmware development for x86 platforms. I developed coreboot, sometimes CDK2. I maintain Braswell SoC, PC Engines platforms, MSI desktops from the recent 12th generation, and I also I'm very much interested in various security technologies and advanced hardware features. And of course, from time to time, I also do slightly higher level stuff like Xen Hypervisor, which I will also show you on this presentation. So a little bit of introduction to what is SRTM and what is DRTM, what is the relation, what is the reasoning of the existence of DRTM. So this diagram shows the typical life of a platform from the power on stimulus to the target operating system or a hypervisor, in our case Xen Hypervisor. So we typically start with the power on stimulus, which causes the system to boot from the static root of trust for measurement. So it is like a piece of code set in stone, which is like performing the initial validation of other stages, the yearly BIOS code. And this is what consists of the static root of trust for measurement. So every stage that BIOS executes is validated and it can be considered trustworthy. However, when it comes to later stages of the boot process, when, for example, we have PCI device enumeration, we enumerate I/O devices, we begin executing option ROMs. These platforms, they may still be trustworthy, but the evaluation of the trust state of the platform becomes so complex and actually may sometimes be almost intractable. And this stage of the platform life is called the gap, because there is a gap in the understanding of the actual platform trust state. And according to Trusted Computing Group DRTM specification, the only ways to actually get out of this gap is to either reset the system or perform actually the dynamic launch, which the DRTM is for. So in our case, if we perform the DRTM, it consists of various stages called DCE preamble, which is the dynamic root of trust for measurement configuration environment preamble, which is responsible for preparing the system to perform a dynamic launch. And then it invokes a special CPU instruction which begins the whole DRTM process. In this diagram, it is called a dynamic launch event. When the dynamic launch event occurs, the execution is passed to the DCE, which stands for the DRTM configuration environment. And this is a piece of code which basically is becoming our minimal trusted computing base to start a new root of trust for our software. And this small piece of software is responsible for measuring our target executable or operating system kernel, whatever we want it to be, and jumps to its entry point. And the software we measured, in our case the Xen Hypervisor, it becomes the dynamic measured launch environment per the TCG DRTM specification. Okay, so how do we actually realize this DRTM for Xen Hypervisor? We use the TrenchBoot project. So TrenchBoot is a framework that allows individuals to build security engines to perform the launch integrity actions based on the boot integrity technologies. To these boot integrity technologies, we may include inter-trusted execution technology, AMD SK init or yet to be created ARM DRTM. And this project helps to incorporate these boot integrity technologies in various open source projects. If you are interested in TrenchBoot, you can also join the Matrix or Slack channels. We have also our mailing lists where most of the discussions about the project occur. Feel free to join and learn more. So what you may actually know about DRTM in Xen already is the Intel's reference implementation for Intel TXT, which was called Trusted Boot. However, Trusted Boot has its own limitations. First of all, it is only suitable for Intel platforms to run the DRTM with Intel Trusted Execution technology. Moreover, it is an exokernel to any software that actually it dynamically launches. So the target kernel or hypervisor has to know about the Trusted Boot existence. And of course, this poses another set of various limitations. Currently, tboot supports only the multi-boot protocol and Linux kernel boot protocol. So there is no other way to actually launch anything else with tboot. And of course, there is no AMD support for the AMD SK init. And it requires much more lines of grub configuration modification than it is necessary, because it basically replaces the main kernel with itself, so it kind of drastically modifies how the boot flow looks like. With TrenchBoot, of course, we aim to support all possible existing DRTMs. For now, it will be the Intel TXT and the SK init and ARM DRTM in the future. And of course, we also want to have more native implementation of the DRTM and the target kernels. So there will be support for actually handling the DRTM inside Xen Hypervisor. Also, it gives us the potential to actually boot with any protocol if you get rid of the trusted boot, because you can incorporate a TrenchBoot in any operating system, kernel, or bootloader. And for a comparison, launching a DRTM on Intel platform requires barely one line of grub configuration to be added. So basically, it is like very much simple operation, assuming that the BIOS has loaded a DCE for Intel platforms. And one of the use cases of using DRTM can be, for example, a Qubes OS anti-evil Maid. It is supposed to help against anti-evil Maid attacks by sealing a secret to the TPM and a special set of PCRs that is extended only by the DRTM process. And these secrets are used by the owner to confirm whether the device, software, or firmware has been tampered with or not. And initially, the Qubes OS anti-evil Maid supported only Intel TXT with TPM 1.2. So it was a kind of, let's say, more than 10 years old technology. But thanks to the TrenchBoot, we were able to extend the support to TPM 2.0 and AMD platforms as well. And here I have a short demo of TrenchBoot running on Qubes OS with anti-evil Maid software. And I have made it on Protectly VP4670 platform, which runs open source firmware. So it's like another advantage, because you can modify everything, fix everything you want, almost. And yeah, I'll just go through the boot flow a little bit and explain what is happening in the various stages. So this is like a standard grab menu when anti-evil Maid is installed in Qubes. So it is booting the default entry for anti-evil Maid, and we can see there's an additional line on the top of the screen which is saying enabling S-launch. So this is the instruction, the command we invoke to grab to actually perform the DRTM. The S-launch is a shortcut from secure launch, and then it is like loading the Xen and DOM0 components like any other standard boot process. And after a short while, we see booting the DOM0 already. And as you can see, we can observe the anti-evil Maid unseal service, which is responsible for unsealing the owner's secret from the TPM using the policy against the DRTM PCR set. And of course, before we can actually do that, we have to provide the storage root key password for the TPM. And of course, if we pass the correct password, the secret is unsealed, as you can see, and we are presented a .p code that we have enrolled during the provisioning process of anti-evil Maid. And if we match the .p code with our authenticator application, we can safely pass the lux key file password, which is like another layer of security in this solution. So once we provide the password for the lux key file, it will unseal the key and, as a result, decrypt the disk we have installed the Qubes on. And after a short while, we also see the anti-evil Maid seal service, which is possibly resealing the state of the platform and is resealing the secret to the current state of the platform in case where something might have been modified, or this is a first boot and we do not yet know the actual expected platform state. And then we finally should land in the DOM0 console after a while. Maybe I'll speed up a little bit. Yep. This is a serial console which is typically not available in Qubes. You have to enable it like manually. But for simplicity of the demo, I have enabled it. Yep. And we can see here there's a special application to dump the event log from the DRTM launch. It is compliant with this is compliant with the FE TCG specification of the TPM event log for TPM 2.0 and for TPM 1.2 as well. Also, on Intel platforms, it really depends on the DC implementation, so of the Intel ACM, how the TPM event looks like. But typically, it is like compliant with the TCG specification on newer platforms. At the end of the output of this utility, we have expected PCR values printed. So these are the values by extending each of the hashes from the event log to calculate the final value. And then we can compare against the PCRs read from the TPM directly. And yeah, this is the fragment of the Xen demask. I'm not sure if I scroll that up. I think not. Okay, I was supposed to show a couple of lines from the demask, but I guess it just got scrolled. Oh, yeah, I caught it. Yeah, so right on the beginning of the Xen execution, we can see 3 additional lines prefixed with S launch, where we reserve the Intel-specific DRTM memory for the event log, for the heap where all the data structures required for DRTM are placed, and the SINIT memory, where SINIT is the actual DCE in the Intel solution. All right. Yeah, the software components I have used are available on GitHub. There's only one quite serious issue with booting right now, because there's some kind of stall very early in the Xen. I suspect that the MTRRs may not yet be restored after the dynamic launch, which drastically slows down the execution. And yeah, a little bit about the progress of TrenchBoot, what we did since the last year. So we have successfully finished 3 phases of the project of enabling TrenchBoot in the Xen Hypervisor and Grub for Qubes OS and anti-evil Maid implementation. These mainly consisted of enabling TPM 2.0 support in Qubes, updating to the newest TrenchBoot patch set that was issued for Linux kernel, and enabling AMD support in TrenchBoot and Qubes OS. Okay, so for the phase 2, in short, what we did for Qubes OS was to basically ensure that TPM 2.0 is correctly supported in Grub and in Xen Hypervisor. We had to add the TPM library for Xen, just for the Xen to be able to measure the DOM0 kernel and initial RAM disks right when it is like being executed. We also had to add the TPM2 software stack to Qubes in order to be able to talk to the TPM, extend the scripts for sealing, unsealing the secret, and setting up the TPM, and stuff like that. When it comes to updating to the newer TrenchBoot boot protocol, there were certain changes introduced to the patch set that was enabling TrenchBoot for the Linux protocol, and it involved changes in the Grub as well, so we had to accommodate for that. So we basically rebased the support we did for dynamic launching with multi-boot protocol in Grub. And then we could proceed with enabling the AMD support for Qubes OS, TrenchBoot anti-evil Maid. And it consisted mainly of updating the secure kernel loader, which is the DCE for AMD platforms. Also, we had to select some better hardware, because initial phases assumed that we will test it on Asus KGP D16, which recently occurred to be too old to run Qubes OS, because launching a domain was timing out already because of various speculative mitigations involved there. So this CPU slowed down so drastically that the Qubes OS was actually not usable. Yeah, so this caused us a little bit trouble, but we found another hardware replacement for that. Thankfully, AMD hardware is very affordable in terms of DRTM, because almost every machine supports that, as long as it supports the SVM. Yes, and again, we also rebased the AMD support we had to the newest patch set for the dynamic launch, and we had to stitch everything together. And yeah, the whole project since phase 1 to phase 4 was sponsored by NLNet. Yeah. Okay, and the hardware we tested it on and is known to work. It's presented on this slide. As I shown on the demo, it is a Protect VP 4670. We tested on also a slightly older Dell Optiplex 7010 and 9010, also with open source firmware coreboot. So it is a kind of unit to test the older implementations which supported only TPM 1.2. And it also worked on an HP EliteDesk 800 G2. Very affordable enterprise mini desktop. And also for AMD based, we also used an HP enterprise mini desktop, HP T630. For AMD, it is like crucial to have a discrete TPM because the integrated TPM in the CPU is not suitable for DRTM due to various reasons of lack of TPM localities. So keep that in mind when you want to select a platform. When it comes to Intel platforms, typically any vPro platform is supposed to support DRTM. So it may be wise to look at vPro platforms first. But also there are SKUs which actually support just Intel TXT. So the DRTM is supported like on the Protect EVP 4670. And yeah, what is still in progress, we would like to extend the pre-built packages of Grub and Xen for other distros as well, because Qubes is not the only target we want to support with TrenchBoot. So we would like to set up repositories for Debian, Ubuntu, and Fedora, at least temporarily until the patches are actually merged upstream. And then we also like to prepare some tools that will assess the system readiness of actually performing the DRTM, because there are often some BIOS bugs that may prevent to successfully launch a system using the dynamic launch. For example, there were situations where users reported that they just are having like a blank screen and nothing happens after the dynamic launch event is issued. So basically, on some hardware platforms it works and sometimes it doesn't, and on certain platforms it may even not work until a BIOS fix is released. So yeah, and we plan to use this tool to actually provide some indications to the users whether they can actually use TrenchBoot and DRTM. And in Qubes we'd like to add such an indicator to the Qubes security report. And the last but not least, the UEFI boot mode support for TrenchBoot, which is gonna be some challenge. Yeah, we estimate the start of the work like at the end of this year, on the beginning of 2025. What we assume to do, actually what we plan to do is to repurpose the legacy multiboot 2 entry for the secure launch. So basically, to get rid of UEFI completely for the DRTM boot path. So the flow should actually look like this, that the grub is doing the exit boot services. We do the dynamic launch. We jump into the Xen dynamic launch entry point, clean up the state after the dynamic launch, and then proceed with the plain multiboot 2 for legacy BIOS. And yes, we also plan to implement TrenchBoot anti-heavy Maid compatibility test suite, which will be a comprehensive set of tests that will thoroughly validate the system readiness to and proper implementation of the TrenchBoot. Also, I plan to give a design session on the implementation of TrenchBoot in the UEFI boot mode, because there are many possible options to actually how we can implement that. I'd like to spark some fire for the discussion how we should actually do that, because maybe the legacy multiboot 2 path is not necessarily the way forward. Some people may also, for example, require secure boot for reasons. So yeah, I would like to hear your feedback, and please join me in the design session if it occurs tomorrow. And thank you. This is it for me. I'm open to your questions. Yes, please.
When are we going to get the Xen patches for this? When are you planning to actually do the Xen changes?
Okay, so the situation is a bit complicated here because initial implementation was done for Linux kernel, and we have some slight troubles on getting an agreement how it should look like for Linux kernel. Not yet. It's
I don't know, by the slides, I assume it was merged into Linux already.
no. It's
Unfortunately, it is a series into Linux that covers 4 major maintainer areas, and they can't agree on how it should look.
yes, and yeah,
There's an implementation for Grub, an implementation for iPixie, an implementation for Xen that's sat in the Qubes patch queue, and we can't actually stabilize the interface until we know Linux aren't going to go and command that it changes.
So the dependency chain is like this. So we wait for Linux approval how the interface should look like because they are very insisting on calling the exit boot services. So we had to give the ability to Linux kernel to issue the dynamic launch. We also have troubles with getting SHA-1 in there because it is old, it is vulnerable, but still the old platforms have to use it. But it's kind of difficult to explain the reasoning. And before we actually Linux kernel agrees on the interface, there are this set of changes for Grub that are actually the base for everything we do. So the chain looks like follows. Linux gets merged, then the Grub can stabilize the interface and get merged, and then based on the stabilized interface, we can actually adapt the Xen changes to it. So this kind of messed up situation a little bit.
Yeah, think about the exit boot services that you said. Xen also likes to be launched without having called exit boot services before. Currently, I'm not saying it cannot change, but that's how it is now.
As far as I know, the native PE entry point, of course, has to call exit boot services, and FE multiboot too as well. Yes, but that is why we are trying to drill into the legacy multiboot 2 path, so that actually we are booting without the boot services already. From what I have analyzed, the boot services are not used so widely in Xen. It was like just retrieving the boot device.
The memory map.
Yes, the memory map,
I
exactly.
think that's the main thing, the memory map.
Yeah, but the memory map and
Also, they like to play a lot with the console.
yes, the early console as well. Yes, these are the things. Yeah, so yeah, these are the things to be considered, and yeah, these are the things to be considered, and that is why I'm wanted to have the design session, because also there's the secure boot reason, which probably is maybe less or more important, depending on the person. Okay, any more questions? Yes, please.
Very nice question. So this TrenchBoot is based on TPM 2.2. Is that correct?
Could you speak a little bit louder?
The TrenchBoot is based on TPM 2.0. Is that correct?
TPM is just a component that is required for DRTM in general. So TrenchBoot can use any TPM that is actually usable. Whether it is TPM 1.2 or 2.0, it depends on the system, because older systems supported only TPM 1.2, but newer systems also support TPM 2.0 or only TPM 2.0.
So the thing to say is that originally TBoot was Intel's reference implementation. It only supports TPM 1.2. It has been
Just in Qubes, to be precise. It was just for the anti-LVMate purpose. In general, TBoot supported TPM 2.0 as well.
okay, but as a project, it's existed with unfixed CVEs in it for 8 years now, something like that.
Possibly.
Basically abandoned it. The TrenchBoot project itself has the goal of trying to upstream support into various things, so into Linux, into Grub, into into iPixie, into Xen, to try and make this kind of easy to use and therefore it will become
Yeah, iPixie, from what I recall, iPixie has similar problems like Linux kernel. Like, why is that? How do you use secure boot with this? That was the main questions when we sent some changes to iPixie upstream repository. So yeah, everything is like UEFI mindset today, and it's actually hard to get around that.
What actually makes it x86 specific in the sense that
it's not one of the things that TrenchBoot
Yes,
with ARM, but their equivalent of this. So
Yep,
it's still a prototype spec, I think.
yes, the specification for ARM DRTM is currently in progress. We have been recently discussing it again on a meeting with the parties that are actually involved in creating the spec. So yes, it is not x86 specific. The Trusted Computing Group DRTM architecture is just a guidance how to implement that for any possible architecture. It's not necessarily for x86.
There are, of course, platform-specific bits on Intel, it's Intel PXT, on AMD, it's the SE infrastructure.
Yeah.
So there are some aspects that are platform-specific, but we're doing our best to
Yep.
do all the bits that aren't platform-specific or architecture-specific to be done numerically so they can be picked up by others. There's proto interest from RISC-V and OpenPower on it a little bit, in that there are some people who've looked at it and said, oh, that looks nice. So it probably will grow beyond x86 and ARM as well in due course.
Okay, I don't know how much time left do I have. It's like 9:40 already. 5 minutes. So any more questions? Okay, I don't see any. So thank you very much.